Hello, everyone. Welcome to part one of our review. We're going to start off with the pre-Chemistry 30 review, bringing everyone's skills up to date. So this is lesson one of the pre-Chemistry review. All right, what we need to be able to do before Chemistry 30 is we need to be able to look at a description of a situation that's occurring and translate that into a balanced chemical equation. Even a net ionic equation. So let's look at that today. So we're going to be faced with different situations, double replacement reactions, basically acid-base reactions, neutralizations, looks like single replacement reactions, hydrocarbon combustions, and we have to be able to take those situations and turn them into balanced chemical reactions. So here we go. It says a solution, now I'm going to underline that, it's a key word meaning aqueous, of ammonium carbonate reacts with a solution, another aqueous, of aluminum nitrate. So we've got to take these and put them into words. So now we know our two reactants, ammonium carbonate, aluminum nitrate. So the first thing we have to do is we have to create the chemicals out of this, the ionic compounds. We know these are ionic because they have an anion and a cation, right? The ammonium in this case is the cation, the positive, and the carbonate's the anion. Same with the next one. Aluminium is the cation, positive metal, and nitrate is the anion. It's negative. So we know they're ionic compounds. We know that probably it's going to be a double replacement reaction if we mix two ionic compounds. So ammonium, you guys should be familiar with that, but it is an interesting cation in that it's the only polyatomic ion with a positive charge. So there it is there, ammonium NH4+. So we're going to jot that down, NH4 charge of +1. Carbonate, on the other hand, is quite common. We can find it here. Okay, it's CO3 2-. Now, how do I know to look on the polyatomics and not at the general periodic table? Well, it ends in ATE instead of IDE. Ending in 8 kind of symbolizes that this is a complex ion. So there's our charge. Whoops, CO3. There we go. CO3, I believe, is carbonate. Yep. Charge of -2. Now on the aluminium nitrate side, let's do this in blue. Aluminium, it's aluminium with a charge of +3. We can find that easily. It's just a metal on, there it is. Atomic number 13, charge of +3. And next we have nitrate. Nitrate, again, it ends in ATE, suggesting that it's a polyatomic ion. It's a very common one. So if we look it up, it's right here. Not nitrite, but nitrate, NO3, with a charge of -1. So let's put that in. Okay, now that we're done that, we can set up the actual molecules. So in order to balance out a -2 ion with a +1 ion, that means we're going to need 2 of those for every one of those to balance the charges, of course, which is really essential when you're making ionic compounds. So here we're going to set up NH4, right? It's got a charge of +1, so we're going to need 2 of them, which is why I put the brackets around and put a 2. That's how you indicate multiple polyatomic ions. And we just need 1 CO3, so we'll just keep that as a single one. Next, we're going to do aluminium with nitrate. So let's take a look at the aluminium. It's a +3, the nitrate's a -1. So of course, we're going to need 3 of the nitrates for every 1 of the aluminium. So let's put that in. Aluminium first, always the metal or the cation first. And we need 3 nitrates. So again, we're going to have to bracket it up because it's polyatomic. There's 1 nitrate. Now we're going to say we need 3 of them. There we go. So reacting those together, we should be able to understand that this is going to be a double replacement. So cation for cation, kind of like this. Swap the aluminium for the ammonium, and let's get going. So aluminium is a +3 charge, correct? And carbonate was a CO3, like that. So aluminium was a +3, carbonate was a -2. Now we have to balance those in our head. Well, how many aluminiums for how many carbonates? Well, what if we go up to -6 and +6? That would mean that we need 2 aluminiums. And to get from -2 to -6, we need 3 carbonates. So what we're going to do is we're going to bracket this carbonate up like this. And we're going to say that we need 3 of them. So that's an interesting compound. Aluminium carbonate requires 2 aluminiums and 3 carbonate ions to work out. Okay, now for the other one, ammonium comes over here and replaces aluminium. So now it's ammonium, NH4 plus 1, with an NO3 minus 1. And so plus 1 minus 1 cancel out nicely. We just need 1 of each, which is why I haven't bracketed up any of these. Just 1 of each cancels out perfectly. Now, last but not least, actually second last, we need to figure out the states that these are in, right? So a solution of ammonium carbonate, that would suggest to us that this chemical is aqueous when mixed in water. It dissolves fully. What about aluminium nitrate? It says a solution of aluminium nitrate, so that would also suggest aqueous. Now, the thing is that we've formed 2 new products, and we need to figure out if those are still aqueous or if they're solid. Because remember, guys, oftentimes you mix 2 chemicals, the resulting solution might become, cloudy as solid particles start basically precipitating. If you remember that word, precipitating means forming a solid in the water, kind of making it cloudy. So let's check aluminium carbonate. Let's go to our solubility table, find it here, and we've got carbonate is here, and solubility greater than, or very soluble stuff, is found here. That would be your ammonium, and that would be your group 1 ions. Aluminium is neither of those, so it must fall in the slightly soluble category here, which means it's a solid, so it doesn't really dissolve that well in water, so that would precipitate out. We'll put an S there. Let's check ammonium nitrate next. So we go to nitrate, there it is here, nitrate. Go down to ammonium. Do we see ammonium here? Nope. So that must mean it's in the very soluble category here most. Okay, so that means that this is aqueous. Okay, perfect. Now, last but not least, we have to balance the chemical reaction. So, how do we like balancing reactions? We always like to start with a molecule that has, an element in it that's only found in that molecule. So, for example, notice how oxygen is found in both reactants. It's also found in both products, which means I wouldn't start balancing with that because it's too complex. Something I would like to start balancing with is something like aluminium, because it's only found in one reactant and one product, so that's easy to start with. Okay, so if we have 2 aluminiums per molecule of this aluminium carbonate, and over here we only have 1 aluminium atom per molecule, that means we're going to need 2 of these molecules, right, to make it work. Let's do nitrate next. Nitrate works. So over here, if we look, we've got 2 molecules, and each one has 3 nitrates in it. That means a total of 6 nitrates, doesn't it? So we go to the right side, and we see here we only have 1 nitrate per molecule. That means we got to put a 6 here. We need 6 of these molecules, right? We're starting out with 2 times 3 here is 6, and we're ending up with 6 times 1 here, which is 6. So aluminium and nitrate is done. Let's do carbonate. So here we said we're going to keep this as just 1 molecule of aluminium carbonate. So if we look carefully, 1 molecule translates to 3 carbonates, right? Okay, we got 3 carbonates there, so we need to have 3 carbonates here. So let's put a 3 there. Since this only has 1 carbonate, and we need 3 of those molecules to add up to 3 carbonates. Okay, so there's 3 molecules of ammonium carbonate. Let's check the ammonium again, make sure it makes sense. So 3 molecules of ammonium carbonate multiplied by the 2 ammoniums in it, that's 6 ammoniums, and that's how many we have right here, right? 6 times 1 ammonium, right? Okay, so everything checks out quite nicely. And I think at that stage, we're done. We're good to go. We can use this for stoichiometry. All right, now it's your guys' turn to try some out. We'll go through an acid-base example and maybe a hydrocarbon combustion example as well.